Thanks, Phil. Thank you all for coming. So in this talk, I'm going to propose a research program. By that, I mean I'm going to fix on a particular problem. I'm going to suggest, I propose to the community, the research community, a particular way of attacking this problem. And it's supposed to be definitive. If the program succeeds, we'll be done with this problem forever and ever. Specifically, the problem is an old one, cache misses. Every now and then you see another paper, but this is a problem that goes back many, many years. So it's an old problem, and I'm proposing something that I believe is going to be a definitive attack on the problem. So it's kind of ambitious. So let's see how far I can push this. This is done together with Zhou Ming and Zhen Dingwen and Liu Yi and Huifeng Qing, who did all the hard work of getting the data. So it's about Mies equations, and what's new about the way I'm approaching this problem is that I'm going at it top-down rather than bottom-up. So first, I need to explain what I mean by that. And it's definitive in a sense that in order to be definitive, I believe it's got to be universal. So I need to explain what I mean by that as well. Once I do that, then I can explain what the program is about. And in our business, every time we come up with something, there's always the question, what's the use? What's the use? So I need to tell you a bit about what's the use if the program succeeds. So it's about the cache miss equation. So first of all, what is a cache miss equation? It's just expresses the probability of a cache miss as a function of the cache size. So cache here, one of the things ambitious about this program is that I'm not attacking any particular one level of the memory hierarchy. I'm saying that this is the way to attack any level of the hierarchy. So cache here has a very is very general. You could refer to the processor cache, the RAM, database buffer, web proxy, etc. Size, memory is cheap. Maybe size is not an issue. No, I still think that it is an issue for various reasons. Even if you have a large amount of memory, one of the things that is coming back into vogue now is virtualization. With virtualization, you still have to allocate the big memory to various virtual machines, so we have to decide how much to give to any one of them. So size is an issue there. If you're talking about consumer electronics, for example, if you have something year big, and you cannot just simply add memory if you want to. So again, size is still an issue. For guys like you, no, certainly for consumer electronics, energy is an issue, but even for Google, energy is also an issue because idle memory is going to consume a lot of energy as well. So I think size is still an issue. Now, although I wrote that equation, or that equation expresses the probability of a miss as a function of the cache size, actually there are a couple of other things that determine the probability of a miss, and namely the reference pattern and the management policy. So the reference pattern, for example, it is a hard problem, and this slide is supposed to explain to you why this is a very hard problem. So one of the things hard about it is that it depends on, the reference pattern might depend on the hardware variation that you have. Whether I'm talking about the data cache or the instruction cache, for example, and whether you are using multi-core threading. It depends on the layout, whether you are, what is your page size, whether you have an index on your data. The application mix, are your processes pipeline or are they running concurrently? If they are running concurrently, do they lock each other out, for example? That's going to affect your reference pattern. what version of the OS you're using, what compiler options do you have prefetching turned on, and the data instance. At one point, somebody told me that the biggest buyers of supercomputing are actually Walmart and Citibank. And these people, for these people, their data is always changing. So the reference pattern is continually changing. So if you try to model that, that's going to be a big challenge. And the whole thing just depends on how you configure it, right? Do you have level 2, level 3 caches? No, these are going to affect one another. Do you have service level agreements that you have to satisfy? So when you look at this whole shebang, it's just not tractable. There are just not enough equations you can write that will completely describe the interactions here. And if you could write enough equations to describe this, you cannot solve it. So what have people been doing? So what they do is what I call bottom-up analysis. They start off with very simple assumptions about what is happening. So typically, they'll fix on some idealized replacement policy, let's say LRU, assume there's no prefetching, etc. So you have some nice, clean policy to deal with. Then they assume there's independence in the reference pattern, and maybe there's just one process, and so you have a very simple reference pattern. You simplify this, you simplify that. That makes understanding the interaction much simpler. Now you can write your equation. Now, of course, the question is, you have this reality here and this model here. How close are you to the reality? So this kind of bottom-up analysis requires an expert. Now, you need to know what is a reasonable approximation, what is an okay assumption, and what is not. So you need the expertise, especially if you have this particular model and you're trying to customize it, right? Even if you build a model for this particular shebang, and then they have another customer that says, no, I also want your model, but his hardware is slightly different, his software is slightly different. How are you going to customize that model to that different configuration? You need an expert who is able to do that. And even if you have already a model, and then tomorrow you decide to buy a faster hardware, or you decide to upgrade the software, now how is your model supposed to reflect that? This requires a lot of work. It's not scalable. In fact, things are so bad nowadays that people like IBM and Microsoft, they've been pushing for autonomic computing, where they want everything to be automatically configurable and adjust to changes in workload automatically. Now, I think about a model that's trying to do that, automatically configure and adjust automatically, is just hopeless. The situation is hopeless. So my point is, let's forget this. It has not taken us very far in the last 40 years. It's not going to take us much further. Forget it. Let's do it a different way. So instead of this bottom-up, assume, and then build up the model this way, let's start from the top and do it now. So how to start from the top down? You find one equation that will work for everything. Okay? Well, work for everything? No, where's the magic? So the magic is, instead of the probability of a miss as a function of cache size, I give you a small number of parameters to play with. How does that help you? Well, if you have built your model for this particular configuration, and then you want to adapt the model for a different configuration, that just means changing the parametric values. Or if you have a model for this and you change the hardware, you change the software, that just changes the parametric values. You want to automatically configure it, change the parametric values, not change the, but no, you can calibrate on the fly the parametric values. Okay, and you want to adjust it because there's a flash crowd, well, okay, dynamically change the parametric values. So all the magic is going to go into the parametric values. all the while the same equation applies. Okay, so this is what I mean by universal. A same equation, but with values with a small number of parameters, and the values change according to the circumstance. So this is the goal, right? Have one equation that will work for everything. What might it look like? So instead of the probability of miss, let me write a different version. Let's do a map and just express the number of misses as a function of the cache size m, and in this case, just 4 parameters. And it's the particular version that I'm going to show here is very simple. The hardest thing about it is the square root. No, nothing fancy. Yeah. What do the 4 parameters? So this one is the cache size here. What do the 4 parameters mean? Okay. So if you plot the number of misses against the cache size, you see that as cache size increases, the number of misses decreases. So the n star here is the co-miss, right? As when your memory size or cache size gets large enough, at some point it will stop going down, and all you're doing is catching the co-misses. So this is the lower bound, and that's the n star there. And then the m naught here is the vertical asymptote. There is some minimal amount of memory that you need in order to run your workload. You couldn't push it all the way to 0. So this one is, the vertical asymptote is the m naught there. Okay. How different is this from previous equations? One of the critical difference between this and previous ones, now, previous equations typically use a power law. So some inverse polynomial, and it goes on and on and on infinitely, keeps on going infinitely, decreasing infinitely. It doesn't identify some maximum memory beyond which the number of misses doesn't drop. So this is the one difference between this, and this guy here is the m star here. It's kind of the ideal m. There's no point in going beyond here because you're not going to reduce the number of misses any further. And if you are lower than this, then you're going to take some hits. Take a hit. You're going to get some misses. Okay. So the only parameter left is the n naught. Now, it's hard for me to explain what n naught actually is. You can think of it as the parameter that captures some critical aspects of the reference pattern, like whether you do prefetching, some critical aspect of the replacement algorithm, like whether you do prefetching, and whether you do dynamic allocation, for example. If you are doing a compile and you dynamically allocate some space, that's going to come in the n naught. So n naught, the way n naught came into being was when we looked at those issues, but geometrically you can think of n naught as specifying the curvature of this curve. And you see in the next, when I show you the data, that this n naught actually is flexible enough to give you very different shapes. So let me just show you the data. So in this one, what we did was run 7 spec benchmarks on Linux. This is not a simulation. We actually measure the page I/O, and we change the RAM size for this. So this is the data, and the equation gives a pretty good fit for the data. This is the horizontal asymptote n star, the vertical asymptote m naught. M star is here, the maximum memory. And this particular curvature is specified by the n naught. Okay. Now, being a spec benchmark, this one is obviously a compute-intensive workload. How about something I/O intensive? So outside of campuses like this, real people don't use Linux, they use Windows. So we wanted a workload that uses this interactive way of using the system. So we had Windows 2000, and we ran the Business Winstone. Business Winstone is a benchmark where they log some user clicking here and there with something like 12 applications, cut and paste from here to there, icons, etc., all kinds of operations. We take this log, and then we play it back at different memory sizes. Okay. And again, you see a good fit between the equation and the data.
In either of these, did you have more data going past MSR?
Did I have more data going past, like this one?
Yeah, so like, did you have a bunch of data points that just went missing for a while?
Yeah, right. So if you remember, if you compare the curvature here and the curvature previously, you see there is a big difference in the curvature. And this one is I/O intensive because if you just look at the horizontal asymptote is already very high. Now, these days, this is very nice, but we wanted to challenge the model more aggressively in the following way. If you have, people do Java and Python and C#, these garbage collected applications. The trouble or the hard part about modeling this kind of applications is that the reference pattern changes with the memory size. See, the typical bottom-up way of analyzing the interaction between the reference pattern and the page replacement algorithm is you assume a particular reference pattern model. Okay, and then you say, okay, the reference pattern looks like this, and it stays that way regardless of the memory size. But that's just not so in the case of garbage collected applications. So here, what we had was Windows 2000 again, but we used Java, and this one is very memory intensive. You see the steep curve, which is very different from the other two that we saw. Yeah. And still the model can cope. So we are pretty happy with this. But remember, I want this thing to be universal. Universal means that it has to apply to anything, right? In particular, the equation has to work for different replacement algorithms. What I've done is try different reference patterns. So now I want to check whether it works for different replacement algorithms. So here we have a Linux workload, and we patch the kernel to try different replacement policies. So here we have FIFO and random, and this one is the stock kernel. And so you have 3 different data sets, and the equation can fit the 3 different data sets with different vertical asymptotes and different M0 values. The N star doesn't change because that's a property of the reference pattern and not a property of the replacement algorithm. Now, the other thing that motivated me just now was that if you have, you want an equation such that even if your hardware changes or your software changes, you can still use the same equation. So let's check that out. So here, what we did was tried. So this curve and this curve both use the same Linux kernel, but so this is a GCC Compilation Benchmark. We changed the GCC version, and the equation changes shape according to the data. And for this and this, what we did was same GCC version, but we changed the kernel. Now, between 2.2 and 2.4, there was a drastic change in the kernel, and the equation reflects that. So I think it looks pretty good in the sense that even though if you have some software versions that go from version 1 to version 2, all you have to do when you are dealing with this equation is just change the parametric values without having to reanalyze the whole thing. Okay. Where's the magic? how is it that this one equation can fit all of these different circumstances? So I need to give you some intuition for this, and this is the intuition. So let's say TRAM here is the average time between entry into RAM and eviction. So think of the timeline here. Think about one page. A page comes into RAM. There's a code miss. The page comes into RAM, sits there for a while, get evicted, and then there's a reference and comes back in, goes out, comes back in, like this. So the black parts are where it's in RAM. You take the average of that. That gives you the TRAM. And the white parts are when it's on disk. Take the average of that. That gives you the TDisk. And R is the number of times you come into RAM. Okay. Now, what I need to do is look at the probability that you read a page that has been evicted. So one way to look at it is imagine that the references are uniformly distributed on this line. Then if the reference comes in here, then there's going to be a miss. If the reference comes in here, there's going to be a hit. So the probability of a miss is just naively the white part over the whole line, like this. Right? The other way to look at it is the first one is a code miss. You don't count that. Because here I'm talking about a page that was previously replaced. So code miss doesn't count. So you subtract that 1, so it's R minus 1 over R. That will give you the P. So you have these two. You massage that. You have this one equation here. And this one equation, notice that in deriving this one equation, I did not make any assumption about the reference pattern nor any assumption about the replacement policy. So I grandly call this the references plus replacement invariant. So the hardest part about analyzing cache misses is this interaction between the reference pattern and the replacement policy. And here I have an equation that is independent, that appears to be invariant, regardless of which one you use for this or that, it's supposed to still work. That's why I call it the invariant. Once you have this, you just add Little's law, one of the standard results from queuing theory, do a bit of juggling around, and you get the equation. It's not too difficult. You can imagine going from the R value to the N value. So that's the derivation behind the equation. When I described the intuition, I in fact did not say anything about the reference pattern, right? It could have been references to a database buffer, let's say. Okay, so yeah, let's try, check. Would it work when I'm talking about not about RAM, but talking about a database buffer, some application object like this one. So here we took some traces. Well, this data generated from real traces taken on commercial workloads. So these guys have access to IBM's database machines, and they had like 12 traces from some huge companies. They did not specify exactly what those companies were, but you can guess between the lines they were things like AT&T and IBM's own workloads, etc. So these are huge workloads. And we did a simulation, and well, actually the data came from them, and we just checked whether the equation would fit their data, and it seems that it fits very well. Now notice that in real data, the data is not going to come down nicely with the curvature is not going to be nice like this. It's going to be up. The curvature is going to change one way, this way, one way. This kind of waterfall behavior. The equation can't catch that. If you analyze the equation only has one change in curvature. So you cannot catch this kind of multiple changes in curvature. But so what the equation can do is to do its best if you have multiple changes in curvature. Yeah. So that's one of the weaknesses of the equation. If it works for the database buffer, why won't it work for a database for web cache? So here, we took some traces from one of the websites in China. This is supposed to be a largest peer-to-peer website, a lot of naughty stuff going on there. And the fit is very nice. So I'm optimistic that this thing works for web caching as well. One thing about web caching is I actually don't know whether the particular trace the student picked for this has this property, but for web caching, there are these additional issues about some file sizes are very big relative to others, and there's this zip distribution where some data, some files are there are many files that are rarely accessed. So there are some differences in reference pattern from the standard ones, but the equation seems not to worry about this. Okay, so remember my objective was to get one equation to work for all kinds of workload, all kinds of replacement policies, and I've only shown you the good news, right, up to this point. But it's unlikely that, that this will work all the time. So this is where the research program proposal comes in. I have enough data to give me optimism that this particular approach to the problem is feasible. So let's see what will work in general. So I propose that instead of this 40-year-old strategy of bottom-up analysis, let's do it the other way around. Do it top-down, and for every cache type, whether it's database buffer or processor cache or whatever, let's derive just one equation for each level of the memory hierarchy. Okay. So that's the program. So in a case, if I'm talking about the RAM or the database buffer or the web proxy, I show you that this particular equation works. Right? But if you have something like a set associative cache, surely it's not going to work. Very simple reason, because the equation that I showed you is one-dimensional. There's just the M, the cache size. But for a set associative cache, it's two-dimensional. You have the number of sets and you have the associativity. So you have to explicitly reflect this two-dimensional characteristic in the equation. So the previous equation that I showed you is not going to work. So what might work? My current favorite is this one. So here I need 5 parameters. The A here is the co-miss. So remember this is the associativity, and this number of sets. These are the 2 dimensions. The A here is the co-miss. P1 here is the probability of a miss if your line, if your cache has only one line. Okay. And then this one here is a stack distance, some standard measurement, standard parameter for reference patterns. And the F and H here are supposed to capture the locality of the reference pattern. Okay. So we tested this. It has to be universal, right? So we tested this on the data cache as well as the instruction cache. And it seems to work. You notice that for the data cache, reference patterns and instruction cache reference patterns are quite different. For instruction cache reference patterns, there are many models out there, because you can assume it's a loop, it's a recursion, whatever, it's a matrix or what, and you can analyze that. But for the data cache, if you are doing tree traversal or pointer here and there, then it's pretty random, so it's very hard to analyze. So despite the 2 different kinds of reference behavior, this equation holds up. But I don't want to overclaim. We took the traces from this particular website, and I found the traces to be not very challenging. So I'm prepared to concede that this is not the right equation, and we need a different equation. Okay, the purpose of this talk is just to propose this way of attacking the problem, and I don't claim that the particular equations that I have are in fact the right ones. So I've explained all the keywords except this top-down modeling. Well, what do I mean by top-down modeling? Okay, so remember this equation that I have, right? And I show you some data that says that it works for the database buffer. But there's something wrong, there's something missing from this equation. At least in the old days, I'm not too clear about what people worry about nowadays, but when you're talking about a database workload, they are interested in questions of the following kind. Suppose I have this server running this workload, m transactions running concurrently. Suppose I increase m to 2m. Okay, so m is the multi-programming level. Suppose I double the multi-programming level. How would that impact the performance? Okay, so they're interested in questions of this sort. But there's no way, this equation doesn't have this kind of an m in it. There's none of the parameters refer to the multi-programming level. So to reflect that in the equation, I have this other equation. So in this other equation, this one is the m. Okay, m is not a right good thing. Number of transactions. Okay, so it's the multi-programming level, and each transaction makes so many requests to so many records. And the equation will look like this. Yeah. And it's quite obvious that this equation was derived from that equation. So the point is this. I have this equation. First, I verify that this equation works for anything, universal. Now, if there's some aspect of the workload that I want to be explicitly reflected in the parameters, then what I will do is I will analyze how those parameters up there depend on these other parameters, and then I refine those parameters into other set of parameters, including the one that you're interested in this case, the multi-programming level. Okay. So, and if that's not enough, you want to refine further, you just go down some more. So this is what I mean by a top-down approach, rather than assume, and build the model up this way. Yeah. Okay. So let me give you some examples of what you can get out of equations like this one. So energy, right? A popular issue nowadays. So in the case of mobile devices, you want to save battery. In the case of large data centers like what you guys have, you want to save money on the electricity budget. All right? So what does the equation do for you? So remember this example that I have just now? The m star here is sort of like, you don't need more than this. So the idea, of course, is to shut down any excess memory beyond that. But in order to do that, you need to have an estimate of what m star is. And the old equation just doesn't give you that. So what does my equation do for you? Well, let's say we have 3 data sets like this, and then you just fit the 3 data sets with the equation. What you get is 3 sets of parameters, and the m star for the 3 sets of parameters are there. You know, the m star is not anywhere on this curve. No, it's somewhere out here, right? But the equation, you will appear in the equation once you do the fit. Okay. So at this point, it's for me to ask the question, right? When I presented this thing in Beijing to the Microsoft people, they have an interesting spin on the problem. So the guy who talked to me was actually somebody working on BitVault. BitVault is some archival system, distributed, huge amount of servers, and because it's the huge number of servers, you can be sure that there are always some of them going down. So because some of them are going down, you want replication. So we have a huge number of servers with replication, and they're all up. So they are burning up a lot of energy. So his question was whether you can power some of them down. Because you have replicas, right? Can you power some of them down? And he wants to look at how the equation can be used to address that question. Now, it wasn't very clear to me what exactly he had in mind. And this is my best take on his question, which is that if you try to go to a particular replica to retrieve a document and the replica was powered down, that counts as a miss. Okay. So then you have, again, you have misses. You want to find sort of like the minimum memory size for the whole system. But minimum memory size may not be a meaningful question for this particular instance. I think what you could do with the equation is that once you have the equation, you can use the equation to calculate the trade-off between, if you have a miss in this setting, right, that costs you in terms of excess latency. So now you want to balance between excess latency and power saving. And the equation will help you do that calculation. So maybe, do you think something like this will work for you guys? You guys have huge data sets as well, right? So I'll be happy to talk to anyone who thinks that this might be useful for you. Okay, so this is talking about memory sizing. When I started, I said not just sizing is an issue, but the share is also an issue. You might have a big memory, but you don't want to partition it, share it among workloads. How much of the memory is you give to a particular workload. So here is the, how can you use the equation to do this partitioning? All right, so you might want to partition the memory for optimization or to enforce certain service level agreement. All right, so let's say you partition into 3 and you want, let's say, just for the sake of this talk, to minimize the probability of a miss, aggregate miss. Yeah. All right, so these are the 3 data sets that I had before, and you fit them with the equation. Once you fit them with the equation, you can use the equation now to calculate, right? You have the aggregate, you have some aggregate probability of a miss. You use the equation to calculate, and you can calculate what the miss probability would be for any partition, right? And calculation is fast. Okay. So once you do that, you completely map the surface, right? This is it's 2-dimensional problem. You have 2 dimensions, and the surface here is the probability of miss. It's not very clear on this particular plot, but I think this one is the predicted one, and this one is the measured one, the real miss. And you see that the equation gives you a good approximation of the real miss. So what you can do with this now is you can do the optimization that you want, locate where the optimum partition is, or calculate the trade-off between different partitions, for example. Another thing that I used to motivate this was this issue about autonomic computing. If you have a sudden change in workload, you want to react to it automatically and dynamically. How do you do that? And I said, by giving you the parameters, you can just calibrate them on the fly. So now let me give you an example. Okay, so for this, I take the database example, TPC workload, and we change the number of terminals, multi-programming level, cyclically. 50, 40, 30, 50, 40, 30. So the miss probability is going to keep on changing if you don't change your memory size, right? And then you have a certain target that you want to hit, some service level agreement, let's say 0.2, some aggregate, this is just one work type, so not aggregate, but just the probability of a miss. All right, so this time is divided into epochs here. And this is the target that you want to achieve. And if you are stable, then because there's a cycle here, the probability of a miss is going to go in a cycle. Okay. All right. So there are basically 3 ways of doing this. One obvious idea is to do gradient descent. You take 2 neighboring epochs, look. So this is a certain memory size. There is a certain memory size, and you look at the p-means for these 2. You draw a line, this is your target, that tells you what the target memory size should be, right? So that's gradient descent. If you do that, you will converge on the target p-means, but you can go through these violent fluctuations for 2 reasons. One reason is that the reference pattern, for example, has randomness in it, and that randomness is going to throw you off every now and then. And also, the workload itself is already cycling. So that's going to perturb it some more. So because of that, you can have this overshooting and undershooting, and it takes a while to converge. So one way of dealing with this is that, well, you have these fluctuations, let's say random fluctuations, right? You smooth them out. If you can smooth them out, the gradient descent will work better. So one way is to use the equation to smooth out the fluctuations. You have this smooth curve. With this smooth curve, you calculate the gradient. That's a more stable way of estimating the gradient. And sure enough, if you do that, then you have convergence sooner, right? But if you have the equation, why even do gradient descent? Use the equation to calculate what the optimum, what the target memory size should be, right? So if you use the equation to compute the target memory size, then bang, in one epoch you're there. So this is how the equations can be, the calibration here happened in real time. So you can do this calibration automatically and dynamically. Yeah.
What was the dynamic variation in M that corresponds with the various epochs there?
Dynamic variation.
So you were computing M, but you're displaying how accurate your miss rate was. I wondered what the overall variation of M was, given that you had a model behind that was sensitive to the various number of terminals per epoch. Was it a 50% variation in?
I never saw the data, so I couldn't answer. I could look up the data. Yeah. One of my students generated this graph, and I never saw the data. Is that an issue?
I just wondered if it was a small variation in percentage of M. I'm just wondering about the sensitivity in the mapping.
Yeah. I should check. Thanks. Okay, so this dynamic adjustment of the memory size. The next thing is the memory share. Okay, so this one, let's say you have some shortage of free memory. So remember, you have this big memory, and you are trying to cut up this big piece of memory and allocate it to different, in this case, virtual machines. And you start up another virtual machine. So suddenly you're out of space. So you want to reclaim some of this allocation and give it to the new virtual machine, right? And you want to do it in some fair way, right? Okay, so you can define, so here's the scenario. You are divided into 3 parts, and you start off before the reclamation from these 3 of them, some unfair allocation, right? In this particular case, you see that the pool number 2 is consistently has a lower P-miss ratio. Here is the P-miss against divided by the co-miss. So that's our measure of fairness. And it's unfair in the sense that one of them is consistently lower than the rest. And also the spread is big, right? The spread is big. You like to narrow down this spread in the ratio. So if that be your objective, you can have other definition of fairness, but if this is your definition of fairness, now what you want to do is free up some memory by taking away some from each one of them and give this to the new one, let's say. Okay. So you can use, once you have the equation, you can use it to calculate. And it's some kind of prorating. You can see some kind of prorating here, except that the prorating is it's not in terms of MI, not a share. It's not in terms of M star, the optimum, so-called optimum, but in terms of this difference between M star and M naught. Okay, so remember M naught is the vertical asymptote, M star is the optimum. So you're talking about this space, not this space, right? You do that prorating, and according to this definition of fairness, you should get what you want. So we did it, and after the reclamation, you see that the square, none of them is consistently the lowest, and the spread is smaller. Okay. So the point here is that once you have an equation, you can use it to do your calculations for your memory allocation management. Okay, one more example. Autonomic computing. I said that the IBM and Microsoft have been pushing it, and in fact, the database people are out there on this. So the major database people, they have all come up with software to help people configure their machines automatically. And for a database server, there are just humongous number of tuning knobs. But for all of them, one of the things that they focus on is the buffer allocation. So all three of them have some simulator embedded to predict the number of IOs for, if you have a bigger buffer or a smaller buffer. And this is you do the simulation to do this, use simulation to do this prediction. So it's hard coding, right? So it's very hard to change if you change the hardware, you change the index structure or whatever, the table design, then how are you going to change the simulation code? So this is an issue. In the case of smaller buffer, so first of all, we have to understand, right? Why would you want to have a smaller buffer? So according to what one of the guys told me, in the enterprise setting, sometimes the buffer manager is a black box. You cannot see the reference patterns. What you can see is what are the misses. You can see the misses coming out of the black box, but you cannot see the reference pattern inside the black box. So now, if you change the buffer allocation to a smaller size, why would you do that? Well, you might do that because of server consolidation. Let's say you take two servers, you put it on the same machine. Each one of them now get a smaller buffer, smaller amount of memory. All right, so you have a smaller buffer, a smaller amount of memory to play with. Now you're going to predict the number of misses. How do you do that? If you don't know the reference pattern, what was previously a miss, what was previously a hit now becomes a miss. And you never saw the hits. So if you never saw the hits, you never saw the reference pattern, how are you going to predict the misses? So for them, this trace-based approach is going to be a problem to attack the issue of smaller buffer size. For me, it's not a problem. I just use the equation, fit it, do interpolation, extrapolation backwards rather than forwards. No problem. Yeah.
So how did you derive M0 in that instance?
M0 just fall out of the fit. It's not derived.
Okay.
So the four parameters, when you give me a set of data, the equation can be massaged into a linear equation. And then I just take your data, and then I fit it, do a regression, I get it. Yeah. So this is what I'm trying to get across. The way people have been doing it, doing cache miss analysis all this while, is what I call bottom-up. I say, give it up. This is not going to work anymore. Let's do it a different way, this top-down way of doing it. More than that, I believe that you can't go on trying to derive a new equation for a new setting. You should try to get one equation that will work all the time. Okay, and the way to do that is through the parameters. So it seems like, offhand, a priori, it doesn't seem like it should work. But I think I have enough data to make me optimistic about this particular approach working. So this is my goal. I would like people to look at this, adopt this particular way of attacking the problem, and I hope that you guys will come along and let's just solve this once and for all. Let's not keep on generating buffer miss equations. This won't go on forever. Okay, I'll be happy to take more questions.
So do you have a notion for, I'll call it the compositional mathematics, that allows you to take one parameter out of your equation and replace it with, say, 3 more higher resolution parameters? So for instance, you started with your base model, you modified that model when you went to the n-stream database buffer. You modified the model a different way when you went to cache set associativity. If you needed to do the composition of database buffers with cache associativity, is there, in other words, is there a kind of a hierarchical refinement that one could imagine where you can reuse some of the fundamental physical modeling parameters from the coarser level and then selectively replace one or two with refined elements so that you're not deriving a new equation for each different instance?
Okay. So the question is, let's say you have a database workload. I have a database equation. I have a cache processor cache miss equation. Is there some way to integrate these two models to give me a new model to predict the cache miss for what is the cache in this case you're thinking about?
Say set associative.
Set associative. Okay, so in that sense, okay, so the way I see it is that I start with the cache miss equation for set associative cache, and I want to see how my database model can help me refine this. Short answer is, I don't know. I've never done it. I don't know how it might work. What the kind of composition that you're thinking about, I've tried to work on, let's say, I have two compilation workloads. No, let's say I take the same file and I run two compilations simultaneously. No, how would the equation can I take the two equations and then and merge them to give me one equation? Things like that. But I've not looked at two different types of equations.
Well, I'm also almost thinking of the taxonomy where you take your initial equation and then in the refined mode you say, in this mode, n0 is no longer a constant. It's replaced by this function and these three additional parameters. And m0 is no longer a constant. It's replaced by this. And so the equation grows in complexity as you've added the parameters, but it does it in a way where you could assume some coarse-grained approximations and then a series of hierarchical refinements that kind of attempt to recapture the intuition slide that you displayed.
Yeah. So your point is, whether I have some kind of theory for doing this hierarchical refinement that I talk about in the top-down thing. Right now, right off, no. The only thing I tried was for the database case. I don't know how that might generalize to other parameters, other workloads. Yeah, thanks. But yeah, if I've convinced enough people to attack this problem this way, you will see the answer soon, I hope. Yeah. No? Okay, thank you.